But so basically, today's topic, the the concept is easy enough. I'm going to be very honest with you. The concept is easy. The thing that's going to make this particular section annoying to deal with, the thing that's going to make this particular section annoying to deal with is the fact that they're going to require a lot of recall here. In isolation, the concept is very simple. It's basically applying implicit differentiation to story problems. And, basically the story problems are going to require you to think something up. And we'll talk about what that means. So, what are we doing? We're going to be able to use related rates to find time-valued quantities implicitly. I'm using implicit here, right? And I wanted to emphasize this phrase time-valued because especially when we're in the sort of application section of all this, when we're dealing with quote unquote real world situations, it's all going to be rates with respect to time. So sort of our default variable that we're working with is going to be t, and we're going to be seeing a lot of things with respect to time, the speed at which they are happening. A lot of stuff is going to be. So just be aware of that. And the thing that's, again, as I said before we got started, a lot of this is going to revolve around, hey, I'm going to need an equation, I'm going to need a formula. And especially, and I'm going to say this to you, if we're in a situation where we're still in the spring doing this remotely and you've got remote AP test, think about, the formula sheet maybe. Because I'll be honest with you, a lot of this stuff, it's literally you're just going to have to sort of pull it out of thin air. Or at the very least, for right now, you're going to need to recognize what you need and then you can look it up, right? And I really do mean this. If you're capable of intellectualizing and doing great on problems like this, the AP exam is going to be very simple because there's no one kind of problem here. Like, we're not going to go in and be like, okay, you're going to see about 5 of these, 2 of these, 3 of these. Every problem's going to be different, and there's basically infinitely many ways to craft a related rates problem. So literally, it's just going to have to be you relying on what you know. Okay, let's start very simple. Working with a related rate. How do we do this? So, what they want us to do is that, maybe X is one of the edges of the shape. And we know that the area of that shape is modeled by the function a equals 8x squared. And whatever it is, the size is with respect to time. So the idea here is probably, hey, the shape is sort of growing and shrinking as you're looking at it. Who knows why, but that's the way that this problem is sort of dealing with this. So what we want to do is we want to write an equation that relates dA dt, the rate that the area changes with respect to time, to dx dt, the rate at which one of the dimensions of the figure is changing with respect to time. So what we're going to do is we're just going to Well, how do we find dA dt? How do we find dx dt? We take the derivative implicitly with respect to t. So, and this is going to be true pretty much for every problem that we do here. Basically, we're taking the implicit derivative of both sides, but instead of being with respect to x or with respect to y, we're doing this with respect to t. So what basically we're going to end up with a extra factor of dA dt and an extra factor of dx dt, right? So the derivative of a is just 1 times dA dt, right? That's on the left. On the right, the derivative of 8x squared is 16x times the derivative with respect to t, dx dt, right? And so now look at what we've done. dA dt equals 16x dx dt. That is an equation that relates dA dt to dx dt. So basically, this is what we're going to be doing. We're going to craft an equation. Here it was given to us. Take the derivative with respect to t, probably, of both sides, and then write out our answer. Okay? I mean, that's pretty much all this is. I think I've got one or two more of this type of situation. Let me push on. Yeah. Now here, they're trying to be complicated. Don't let it be complicated. All they are telling you with this and with this is that x and y are functions of t. And so when we take the derivative, they're not like constant. They don't just go away, right? That we have to do this implicitly, right? So let's do it. We're going to take the derivative with respect to t of both sides. So on the left, we're left with dy dt equals, take the derivative of x squared, that's 2x dx dt, plus the derivative of 1, which is just 0. And now look, they want us to find, so like this should be a reflex. I'm not even saying like there's stuff to do before here, but like when you're trying to work with this section and stuff like this, if you know that you're working with in terms of t, taking the implicit derivative with respect to t of both sides should be reflexive. So now look at what they're telling us. They're telling us that we want to find dy dt when x equals 3. And if we look up here, they tell us that dx dt equals 2. So let's look at all our variables that we have here. dy dt, that's what we're looking for, right? X and dx dt. Well, what's x? X is just 3, right? What's dx dt? Isn't that just 2? So let's just plug everything in. dy dt, which is what we're trying to find, is the same as 2 times x, and x is 3, times dx dt, and what is that? That's 2. So dy dt is 2 times 3 times 2, which is 12. Pretty simple. If you can do this problem or this problem, you're going to have no issue with how this works. These are the basic skills that we're going to need to figure out what the answer is when it comes to a story problem. All right, here's another one. Assume that all variables are implicit functions of time t. So again, we're taking the derivative with respect to t implicitly, and we want to find the indicated rate. We want to find what? We want to find dy dt. So let's do this. Take the derivative implicitly of everything. Derivative of x squared is 2 x dx dt. The derivative of 5y squared is 10y dy dt. The derivative of 4y is 4 times dy dt, right? And the derivative of 50 is 0. So what we need to do is we need to solve for dy dt. Well, first thing we should probably do is get all the other stuff over to the other side. Let's subtract the 2x dx dt over and factor out the dy dt. There we go, much better. And then we can divide that over. And then just plug everything in, right? We know what x is 7. We know what y is, it's -1. We know that dx dt is 3, so we can just plug all those things in. Two times 7 times 3 all over 10 times -1 plus 4. So we got this is 42. Negative 10 plus 4, that's a -6. Negative 42 divided by -6. The two negative signs cancel out and we are left with +7. That's one way of sort of organizing yourself. First, solving for dy dt, then plugging stuff in and getting your answer. If you like that way, that's great. You can do it that way if that organizationally works for you. I also am totally fine. I mean, I don't care. However you do it. But like, if you would rather instead plug stuff in before you start doing your solving, that totally works too. If you want to solve first and then plug stuff in, do it. If you want to plug stuff in first and then solve, you'll still get the same answer. Well, what did we say the answer was 7, right? And in fact, sometimes if you plug it in, the numbers get so much easier because we know what x is. X is 7. We know what dx dt is. That's 3. We know what y is. That's -1. And the other great thing is once you get here, if you want to, instead of having to write out dy dt over and over and over again, if you want to change that to a different variable that requires less physical writing, you can do that because who cares, right? You're just trying to solve for the variable thing. Whatever that variable thing is, you can do it. But like, this is 42. I'll call it z instead, right? Now I've turned this into an algebra 1 problem, right? This is 42 minus 6z equals 0. Add, divide, it's supposed to be a t, can't draw. And it's just the same number I got before, right? So it really doesn't matter how you do it. The only thing is, here's what I will say. The only thing that you have to do first is you have to do the implicit derivative first before you start plugging stuff in. Don't plug stuff in until you've taken the derivative, and then you should be good. You know what I'm saying? because you need to generate all your dx dt's and dy dt's and see what x's are left and what y's are left and all that sort of good stuff. Okay? But once you do this, however you feel like you want to get to the answer, as long as you get the same answer I do, you're almost certainly okay. Yeah? So some of you may prefer to plug in first and then solve. Others of you may prefer to solve first and then plug in. It's up to you. All right, now let's get into the story problems here. These application problems. So here what we have is something stolen from physics. And this is absolutely true. The equation V equals I times R is an equation that pops up in electricity and magnetism in physics. The number of volts is equal to the current times the resistance of the resistors in the circuit. That is to say, like you look at the battery, you know how many volts there are that are going through the wires. You look at the resistors, you can figure out the resistance. The current, the quantity and the power of the current is based on how big the voltage is and how big the resistance is. All right, so that's actually, and that's how they send electric current along. They will make sure that they like all of you have seen a transformer, right? Those little boxes that sort of dot neighborhoods and places. What they do is they step up or step down the voltage to create current to push to people's houses and stuff like that. So what they're telling us is they're giving all this information, but let's start, before we do anything else, let's start by making the equation that we're actually going to use, because this is sort of our base equation. This is the equation we're going to generate from, but we're going to implicitly derive and get our answer. So dv dt equals, well, we've got I times R. We're going to have to use the product rule. Left d right plus right d left. So let's look at the information that we have. Now that we've got our equation, right here, let's look at the information that we have. Well, okay, we know that V is increasing at the rate of 2 volts per second. Now that's not the voltage, right? That's the rate of the voltage. This is dV dt. Increasing at the rate of should tell you it's a derivative, right? Or decreasing at the rate of. Or if they tell you volts per second, that should tell you dV dt, right? So look, what we've got dV dt is increasing, that's positive, at the rate of 2 volts per second, while I is decreasing at the rate of 1/2 of an amp per second. An ampere being the unit of current. So again, rate of, so we're talking about di dt. And that is decreasing, so we know it's negative 1/2 amp per second. We know that t denotes time in seconds, and so we want to answer the following questions. Find the rate at which R is charging when V is 16 volts and I is 4 amps. So we want to find the rate at which R is charging. We want to find dr dt. That's what we want to find. So let's take stock of all our variables that we have in our equation here. Do we have everything we need? We've got dV dt, that's 2. We've got dr dt, that's what we're trying to find. We've got I, right? They tell us here, v is 16 and I is 4. So let's write those things down too. Let's not forget. So we've got I dr dt is what we're trying to find. The idt we have, dv dt, but we don't have r. We need to figure out what r is, otherwise we can't do any of this, right? So let's step back for a second. How do I find r? Well, let's look. Okay, I've got all this. Well, wait a minute, hold on. Here's another equation with r in it. I know v, I know I. Can't I just find r that way? Right? So if I want to find what r is, v divided by I, right? I divide the I over. So v divided by I, this is 16, this is 4. So r had better be 4, right? And by the way, for those of you who didn't see it up here, ohms. Sometimes I often see this instead of just the word ohms. I've seen it, the symbol as a little capital omega. That's where that comes from. So now we have R. So now that we've collected ourselves, look at what we have. We've got dv dt, we've got I, we've got dr dt. That's what we're trying to find. We've got R. We figured out that that was 4 using information we already have. Di dt, we've got that. So now we can solve. So once again, do you want to plug in first and solve? Or do you want to solve first and then plug in? It totally doesn't matter. You do you. For one like this, I'm going to plug in right now just because I don't want all these letters. I want one letter. So 2, that's dv dt, equals, what's I? 4. What's dr dt? That's what we're trying to find. I'm going to label that x. Okay? You don't have to. You can either leave it as dr dt, or you can choose any sort of token variable that you like, as long as it doesn't confuse you. I don't care. It's all good. What's r? That's 4. What's di dt? That's -1/2. Now, once again, this is turned into a basic algebra 1 problem. 2 equals 4x plus, oh, 4 times -1/2, that's -2. So I'm going to change that to a minus sign. And just solve for x. So x equals 1. And what was x again? Well, let's make sure that we are communicating correctly. X was the rate at which r is charging. That is to say, dr dt, that's 1. Our units, well, r's units are ohms, so the rate is going to be ohms per time, right? In this case, we're talking about seconds, right? All these are in seconds, so and 1 is a positive number, right? So now the second question, so that's question number 1. Find the rate at which r is charging. Well, we did it. Ta-da! So now they're asking, is r increasing or decreasing? Is the resistance in the circuit getting bigger, or is it getting smaller? Well, if we look, the rate is positive. The speed is positive. If you're driving a car and your speed is positive, are you going forward or are you going backward, right? You're going forward. So if your rate is positive, it's increasing. If the rate is negative, it's decreasing. If it's 0, it's staying the same at that point. So here, the answer to part 2 is increasing. And, you know, on the AP exam, it might behoove you to write a whole sentence. And in fact, I'll tell you, for a problem like this, I will give you the answer that will get you 9 points on this problem. At the time when V is increasing by 2 volts per second and I is decreasing by half of an amp per second. And notice decrease, I said decreasing, so did I include the negative sign? No. Decreasing already implies the negative sign, so don't say decreasing by a negative number, otherwise you're double negative, you're saying it's increasing by half. So don't, just be careful. So at the time when blah and blah, R is spelling SI increasing by 1 ohm per second. You put that answer on the AP exam because this is a perfect free response question right here. Perfect free response question. If you put that for your final answer for all the work, that would be 9 out of 9 right there. If you can do this, write down the variables along the side, solve for the missing piece, have your equation, plug in, solve for x, write this out like this, and then say this. That is a 9 out of 9 right there. You can do that. Each and every one of you in this room is capable of doing that. And it's simple. But I guarantee you, if you can do this, you can do literally everything on those free response questions. Let's do a bunch more. I think we've got like 3 more. When a circular plate of metal, so again, right off the bat, they tell you exactly what you need to know. Circle, right? Circular plate of metal is heated in an oven. Its radius, well, okay, I'm going to write, before I even do anything, I'm just going to write that down. Its radius increases. Oh, so there's the rate too. I'm going to write that down. Increases at a rate of 0.01 centimeters per minute. So that's R and dr. At what rate? So again, we've got a d something dt. Is the plate's area. Okay, so now we want dA. Right? So automatic. So now that we even better, we know A, right? Area. Area of a circle. Well, we know that. Right? Pi r squared. Area. So this is all, I haven't even finished reading the problem yet, right? Increasing when the radius is, okay, so here's what the radius is 59 centimeters, right? So let's do this. So, okay, we want dA dt. Well, let's generate dA dt. Let's implicitly derive both sides. Pi is a number, so don't do anything with that, but r squared, that's our That's our variable, so the derivative is 2 pi r. By the way, this should look familiar too, right? 2 pi r, isn't that the formula for circumference? Guess what? The derivative of area is perimeter. And we took the derivative of r with respect to t, so dr dt is there too. So now look, do I have dA dt? Yeah, that's what I'm trying to find. Do I have r? Sure do. Do I have dr dt? Sure do. So I'm going to leave it in terms of pi. Under no circumstance, unless they specifically tell you on the AP exam, which like I haven't seen necessarily before, except like they'll ask a question in a certain way where you sort of have to in order to get an answer that really makes sense. But if they don't specifically give you directions to like put this in a calculator and round it, don't. That's extra work. 2 times 59 times 0.01. Well, okay, this is 2 times 59 is 118. I'm having anxiety. Did I get that right? 5 times 2 is 10 plus 1 is 11. Hey, yeah, 118. And then times the 0.01. That means that just means 0.01 is a great number because that means we can just take the decimal place and move it over 2 because we're dividing by 100, right? 0.01, this is 100th. A tenth, 100th, right? So look at what we have. We've got 1.18 pi. And what are our units? dA dt. The area with respect to time. Well, what's area? Let's look. Oh, they tell us centimeters. So area is cubed, right? No, area is squared. I'm sorry. Don't mind me. I'll see myself out. Area is squared, right? Centimeters squared per, what's our time unit? Minute. And again, free response question. When the radius is 59 centimeters. And let's even include the rate of change of the area when the radius is 59 centimeters is 1.18 pi centimeters squared per minute. And so, like, if you're crafting a good free response answer, your answer should ask the question, when, how many, and what unit, right? Right? When? When the radius is 59 centimeters. How many is it? It's 1.18 pi. That's the growth rate. What unit? Centimeters squared per minute. If you can answer those 3 questions on your paper, guaranteed you're probably going to get a 9 out of 9. So make sure you do all of those things. Okay, this one. This is sort of like 3 problems in one, so we're going to do these one at a time. So it really, really, really does help to have a picture here. So like they want a wall or a house or whatever. And here's the ground. And then there's a ladder and it's leaning against the house and it's slowly slipping. It's that situation where, you haven't replaced the feet in a while and it just doesn't hold the friction anymore. Or worse, the ground is all slippery. And so you're leaning it up against the wall and you just see it sort of go tick, 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 and it's trying to fall down. So, one thing should be abundantly clear before we continue. This is a right triangle with sides A, B, and C. Whenever you see a right triangle, there are only two possibilities for what you're doing. If you're working with sides, you're almost, I'm going to say 99.99999% going to be using the Pythagorean theorem. If you are not, and you're working with like an angle or something, then we're probably talking like a trig function, sine, cosine, or tangent. Don't try and be cute and use secant, cosecant, and cotangent. Nobody cares. Sine, cosine, tangent. Stick with geometry level stuff because ain't nobody got time for that extra. All right, so let's look at what we have. When we do this, I always write out everything. And I'm just looking at part A. I don't even care about part B or part C yet. I'm always going to do this because whenever you've got a right triangle in a problem, 9 times out of 10, you're looking for a side. And the best part about this is if you notice, we're talking about rates and stuff. One of these sides doesn't change. So like the ladder is falling down the house, right? They're going to give us a state, a 10-foot ladder. That's the ladder. That's 10. Is leaning against a house when its base starts to slide away. By the time the base is 6 feet from the house, so we're talking about down here, that's A. The base is moving away at the rate. So now we're talking about the rate here. How fast is it moving away? 8 feet per second. Well, that's the rate of A, so that's dA dt. So I'm already working on 3 of these. Let's try and figure out what the other 3 are going to be. Okay, so that's all the information we've got. Let's see if the prompt for part A gives us any more information. What is the rate of change of the height of the top of the ladder? Oh, well, so they're telling us that the rate of change of the height. So this is dB dt. That's what we're looking for anyway. We don't need to figure that out. So we still need to figure out what B is and what dC dt is. Otherwise, we're not going to be able to solve this. Well, what's B? How do we figure out what B is? We know A is 6 and C is 10. Well, aren't we using the Pythagorean theorem anyway? How do we find B? Don't we just plug in and find, right? A squared plus B squared equals C squared. Right, subtract and then square root. And we're working with distance, so we don't need to worry about no negative sign here. So we know that B is 8 feet. Another option, if you remember your Pythagorean triples, this is a 3, 4, 5 triangle, 6, 8, 10, ain't it? But that's neither here nor there. So now the only other thing we need to figure out is dC dt. And this, I think, is probably the most, like, if you can get this part, you've got the crux of the entire problem. Because how fast is the length of the ladder changing as it slides down the side of the house? It's not, right? The ladder doesn't change. It's a ladder. We're not talking about one of those extension ladders or whatever. We're just talking about, like a dumb wooden ladder. You just right up against the house, and then it's not going to change. So if it doesn't change, the derivative here, dc dt, is just 0. So look, we've got a dA dt, b dB dt, c dc dt. We've got everything we need. So let's do it. So look, we're going to implicitly derive a squared plus b squared equals c squared. So we've got 2a dA dt plus 2b dB dt equals 2c dc dt. And again, you can just plug everything in. 2a, 2 times 6 times dA dt, which is 8. And this is feet per second. I don't know why I just put feet. Plus 2b dB dt. Well, 2b, 2b, and dB dt is what we're trying to find. I always replace with an x just so that I'm sort of singularly focused. I like to be focused on what's going on. You don't have to, but I'm telling you that's the way I do it. 2 times c, which is 10, times dc dt, which is 0. Then I'm just going to clean everything up, right? 2 times 6, whatever that is, 12 times 8. $96, yeah? Yeah. And 2 times 10 times 0 is just 0. So I'm going to subtract the 96 over. Divide both sides by 16. And get -6. So once again, finish up the problem by saying when the base is 6 feet from the house, the height is changing at a rate of -6. And what's our units for rate? It's feet per second here, right? Ta-da. And notice I said changing. I didn't say increasing or decreasing. I'm going to be very honest with you. The word changing is a really great weasel word. It means that you don't have to think about what's going on and you can just follow the problem's numbers, right? If you do this with the word changing, you don't have to think, well, does it need to be positive? Does it need to be negative? What have you? If you've done all the work and you've translated it properly into here, everything should just come out in the wash. And the word changing helps you to sort of avoid dealing with extra stuff, okay? Now, we are working in this point in time, so all of these things here are already good, right? I can even, let me put this down, -6 feet per second, right? So look, we've got all this information. I'm gonna leave this. I'm gonna erase all my work from here, but I'm gonna leave this info behind, right? So, but I'm gonna get rid of this because we don't need it anymore. And obviously, if this is something you need to copy down, I'm recording. You're watching this on YouTube. You could have paused the video already. Okay, so let's look at part B. At what rate is the area of the triangle formed by the ladder, the wall, and the ground changing? Then, right? Let me keep this picture so that I'm not being confusing. There we go. So area of the triangle rate. So what we're looking for the rate of area, right? That's what we're looking for now. So let's make an area formula. Well, area of a triangle is 1/2 base times height. Well, the base is A, the height is B. So I'm just going to do that. Okay. So now let's find the rate. Let's find dA dt. No, the area dt. And then once again, we've got a product rule. So lefty right plus righty left. So 1/2 b times dA dt plus 1/2 a times dB dt. And look, we know what b is. We know what dA dt is. We know what a is. We know what dB dt is. Don't reinvent the wheel here. You've used this information already. Just put it back in. That's why I had it written here. I kept it written here so that we didn't need to do any more work now, right? So look, let's figure this out. 1/2 of b, well, 8 times dA dt, that's 8. Plus 1/2 of a, that's 6. Times dB dt, that is -6, right? So we've got 8 times 8 is 64, divided by 2 is 32. 6 times -6 is -36, divided by 2 is -18. And so dA dt is 32 minus 18, which is 14. 14 what? Well, area, so it's not just feet, it's feet squared now, right? And then it's a rate, so it's per second. 14 feet per second at that time. Obviously say the other words, but at what rate? All right, so we've got, I'll even leave this here. Who knows? It could come in handy. Oh, you totally could. You totally could do it with that. I'm not gonna, you don't have to, but it should very well be. It should very well be that this does work. In fact, let's do this a bunch of different ways just because we can. Why not? Right? We only have one more problem. So look, at what rate is the angle between the ladder and the ground changing? So that's what they want in here. Normally, angles are handled using Greek letters. I think your book likes theta. You can use alpha. You can use beta. You can use whatever you want. Remember, theta is like a one of those Wiimote steering wheels, right? It's a circle with the little bar in the middle. That is what a theta looks like. Or a Pokeball, for those of you who are so inclined. That's sort of what I think of when I think of a theta. but any Greek letter will do. That's what they use. Doesn't matter. I don't care. You know. So we want to figure out this guy. There are 50,000 billion ways to do this, and each and every one of them should give you the same answer. I don't care which one you do. You do you. So you could do any equation you want, as long as it involves this angle right here. First thing, you could use sine, right? Well, what's b? Opposite over hypotenuse. What's b is 8 over 10, right? Because you need to find the angle so that you can get the the d theta dt, right? So sine inverse of, let's see what that is in our handy dandy calculator. So if they did this to you, that it would have to be during a calculator section, because we can't find angles like this by hand. Let me stop presenting for a second and pull up the entire screen so that y'all can see what I'm doing. Like that. And so we want to find inverse sine. So second sine, get the sine -1 there. 8 over 10. Close your parentheses, get your answer of 0.927295218. I would always use as many decimals as possible. I'm going to just scoot you off screen so I can write this down. Again, if you're doing this in a calculator section, also make sure that you're in radians. Make sure that you're in radians, because radians is the units that they default to on the AP test. So if you're not in radians, guaranteed you're wrong. Guaranteed. So now let's using our equation, sine of theta b over c. Can I do that? Yeah, I think I can do that. We're gonna take the derivative implicitly. So derivative of sine is cosine times d theta dt. That's what we're looking for. And then b over c, we could use quotient rule, low d high minus high d low over low squared. Low d high minus high d low over low squared. So this is b is 8, a is 6. So cosine of theta, well, cosine is a over c. So this is actually 6 over 10. We can save ourselves some time trying to plug that back into the calculator. Ain't nobody got time for that. Times d theta dt, that's what we're trying to find. I'll leave it as an x. C db dt, so 10 times -6 minus b times dc dt, that's 8 times 0, so we can just ignore that, over c squared, which is 100. So now I'm going to just solve for x. I'm going to multiply both sides by 10 over 6 to clear out that fraction on the left-hand side I don't want. And we can figure it out here. Well, you got negative 600 on top. And I don't want to do an equal sign. I want to do an arrow because I don't want a attachment error. 100 over 100 times 6 on bottom. 600 over 600 is negative 1. So x, what am I doing? I'm finding the d theta dt. The angle rate is changing. Radian per second. And I bet you could do this with any other number of equations, actually. I bet you could. But this is good enough right here. Should get this for our answer. All right, I think we've got one more problem. Sand falls from a conveyor belt at a rate of 12 meters cubed per minute onto the top of a conical pile. So we're looking at a cone for our thing right here, right? A cone. And I'll tell you, this meters cubed per minute should be a hint to us that we should want to use the volume. Meters cubed, right? Volume. Right? 1/3 times the area of the base times the height. So the area of the base is a circle. So pi r squared h. The height of the pile is always 3/8 of the base of the diameter. Oh, that's information. The height is always 3/8 of the base diameter. Now we have an r here. We don't want no d. So let's rewrite this. Diameter is 2r. So let's rewrite this as 3/8 times 2r. And if, this 2 here cancels out a little bit down here, so we can rewrite this as 3/4 r, right? So that's information. We're going to hold on to this information for a moment. So let's look at what they're asking for. How fast are the height and the radius changing when the pile is 5 meters high? Okay, we know we need some rates. Let's make our equation. Take the derivative implicitly. Let's do with respect to r first. Lefty right plus righty left, right? So we've got 2/3 pi r h dr dt. And then take the derivative with respect to h, 1/3 pi r squared dh dt. So we want to know how fast are the height and the radius changing, right? That's a lot. There's a lot of stuff that we don't have. There must be a way that we can make this simpler, right? This is ugly. This is gross. I don't want to have to do this much work, especially when I really don't get much. Look what I get. I get meters cubed per minute. So this is the dv dt. That's good. That's our d volume dt. That's set up. I get h, right? But I don't get r, do I? Well, I could plug it in, couldn't I? Five equals 3/4 R. So 20 over 3, right? But now they want to know how fast are the height and the radius changing at the same time. I can't do that on my own. I can't do that on my own. So here's what I'm going to do instead. I'm going to be very, 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 very sneaky. I'm going to hold on to this because this is important. We're gonna hold on to this because once I have everything I need, I can plug it in for the other one. But I need to find a way to make it so that I don't have both of these at the same time because I need to find both. I don't have both. I need one to get the other. So let me do this. Let me rewrite the volume so that I only have one variable. How do I do that? Well, I know that H is the same as 3 over 4R. So what if I took H and replaced it with 3 over 4R? Can't I do that? R squared times 3 over 4R. Well, now I've got another R in there, so that's R cubed. And I'm multiplying 3/4 into this. So 3/4 times 1/3 is 1/4, right? Sorry, 3/4 times 1/3 is 1/4. Yeah? Right, 3 over 12 simplifies to 1/4. So what we've done in doing this like this is we've created our own special little bespoke volume formula for this specific cone in this specific situation. See, now I can do this. I don't have any H's to worry about creating this extra term. So instead of using this one for right now, I can just take the derivative of this one. Right? Bring down the 3, that's a 2 now. So this is our special bespoke cone equation. And we can find dRdt now that we have all the other stuff, and then we can go back in and find the HDT. So let's look. Okay, so dV/dt, that's 12 equals 3/4 pi times r squared. Well, r is 20 over 3, so 400 over 9. And we're trying to find dRdt, so I'm going to make that x. All right, let's do this. I'm going to make life easy, and I'm going to cancel out some factors since this is all multiplied, right? The 3 and the 9 cancel out a factor of 3. The 4 cancels out with the factor of 4 and the 400, leaving me with this. 12 equals 100 pi over 3 x, and then I can just reciprocal, get the 3 up there, divide by the 100, 36 over 100 pi, which if you want to simplify that, I think that's 9 over 25 pi. So that's, what was I finding? dRdt, right? This is dRdt. Well, hey, now I can plug everything in. So I've done all this. Let me scooch all this up. Let me scooch all this up. Is this gonna let me take? Is this gonna make me take everything? No, it's just gonna make me take that. I don't understand why. Stop. Okay, you know what? Forget it. So this is what I have. I've done all my work here. I've got all that. I have used my bespoke volume formula that I created for this specific situation. Now I'm going to say goodbye. Marie Kondo, I don't need it anymore. It's dead to me. Thank it for its service and move on. Because now I have everything I need. I know what R is. I know what H is. I know dRdt. I know dVdt. All I need to find is dHdt now. So let's do it. So 12 equals 2/3 pi times R times H times dRdt plus 1/3 pi. Well, what's R? I'm putting in R like I don't know what R is. It's 20/3 squared, right? Times this thing that we want. I'll label it X again. So let's clean this up because this is ugly, right? This is super duper ugly. But look, on top we've got 2, pi, 20, 5, and 9. Ain't it? On bottom we've got 25, 3, and 3. So let's clean this up. I see that there's a 9 on top and a pair of 3s on bottom. Let's get rid of those. They dead. There's a 5 on top here and 1 factor of 5. And 20 has a factor of 5 too, right? 5 times 4. So let's crack that out. And all my denominators. Oh, and then there's a pi on bottom and a pi on top, right? Pi, pi. All my bottom stuff is gone. What am I left with? 2 and a 4 up on top. Yep. And now let's take care of this one. 400 over 9, and then another 9 on bottom is 27. 400 pi over 27 times x. So let's do the easy part. Subtract 8. This leaves us with 4 equals 400 pi over 27. And I can multiply the 27 divided by the 400. And if you do that, you should get that x equals 27 over 100 pi, right? Because the 400 and the 4 are going to cancel out. Yeah. And this is also in meters per minute. Just like this one was, meters per minute. So first of all, the level of difficulty of this one is made larger by the fact that we have two different variables that we're trying to find at the same time, right? Ordinarily, a problem like this, you would go through and you don't have to do all of this extra. You're just trying to find the rate of the height increasing or decreasing or whatever. And so what you would do is you would, make your bespoke equation kind of like what we did here. And you would do like what we did there just the once, and you wouldn't have to go back and find the other one. I specifically chose this one because this one is a gigantic pain in the butt. And it's important that you see the gigantic pain in the butt that this is, okay? I mean, other than that, good job today. Related rates are easy once you figure out the equation you have to use. They're easy once you figure out the equation that you have to use. And if you can figure out that equation, and then work with it implicitly like we have done, just follow your nose and everything should come out in the wash every time.